So welcome to the next unit in physics, electromagnetic induction. So these are the learning objectives for the unit. You are to understand that a voltage is induced in a conductor or a coil when it moves through a magnetic field or when the magnetic field changes through it. Describe the factors which affect the size of the induced voltage and describe the generation of electricity by the rotation of the magnet within a coil of wire within a magnetic field. So let's look at the generator effect. If a conducting wire cuts at right angles through a magnetic field, a voltage is created or induced across the ends of the conductor. If the wire is part of a complete circuit, a current is induced or created in that wire. Okay, so here we have it. We have a bar magnet here, and a wire is moving up and down, and you can see, well, you can infer that a current is being generated. This is also called electromagnetic induction. The size of the induced voltage increases when the speed of the movement increases of the wire, when the strength of the magnetic field increases, and when the length of wire inside the magnetic field. Okay, that's important. Length of the wire inside the magnetic field increases. So the equation for the induced voltage is V equals mu VBL. Okay, you don't need to know the equation itself. I'm just using it as an example to illustrate how you can increase or decrease the induced voltage. Okay, so V is for volts, voltage in volts. V is the velocity of the wire moving in meters per second, and B is the magnetic field strength in Teslas, and L is the length of wire in the magnetic field. Okay, that's the important thing. So those are the three things that you can adjust to increase the voltage being exerted in the wire or induced. So this is the example. So you have a coil of wire connected to a voltmeter, and you're going to move the magnet up and down through the coil, and what you'll see hopefully is an induced voltage. And if the direction of motion is changed, so rather than moving the magnet up and down, you're moving it down and up, okay, then the voltage will be reversed, and also the induced current. will be inversed. And the generator effect also occurs if the magnetic field is stationary and you are moving the coil. Okay. Which is what we kind of saw last week. So how is this used in practice? Well, it's used in something called alternating current generators. So most electricity produced in the world is used using the generating effect. So the simplest generators and types used in power stations produce an alternating current, AC, which we looked at earlier in the electricity unit. Okay, so it's where the current moves in one direction for an amount of time and then moves in the opposite direction for another amount of time. And this is a plot of the voltage between the brushes. Okay, and after one complete turn of the coil, you'll see that it's going up and down. It's alternating in terms of plus and minus the voltage over time. Okay. So essentially it's like an electric motor in reverse. As the coil is rotated, electromagnetic induction occurs. And this alternating voltage is induced inside the metal coil between the two magnets, and the alternating current is drawn through two slip rings, which you see. Yeah, two slip rings. And the voltage created or induced can be increased by increasing how many times the coil rotates, increasing the strength of the magnetic field, or increasing the number of turns happening on the coil. And an example of that is the bike generator, probably, which you might use on your bicycle at night time for the torch. Okay, so what happens is that when the wheel turns, the magnet is made to rotate, okay, because it's got friction connection to the bike wheel, and it's right next to a fixed coil of wire. So electromagnetic induction occurs and an alternating voltage is induced in the coil, so the coil is staying in the same place, but the magnetic field is changing in its direction, moving from north to south and then rotating to be south to north. This causes an alternating current to flow to light the bulb of your bicycle. And that's an example of an AC generator in real life. And that is pretty much electromagnetic induction in a nutshell.